Hi, I'm Alec Louque, and today I'm going to be giving a lead experiment on experiment 3, the refrigeration cycle. So the experimental objective is to conduct a thermodynamic analysis of the heat pump. First, we're going to be measuring the coefficient of performance, which is the heat load over the work of the compressor. And then next, we're going to be describing the vapor compression refrigeration cycle and a pH diagram. So this is the apparatus. As you can see, it has a lot going on. The orange is actually what the coolant's going to be. This is just your water coming out of your evaporator and your condenser to help the flow. A few things that you got going on. You got some temperature sensors and pressure sensors. That's to be taken for later when you're conducting your coefficient of performance on the cycle. So this at the bottom, that AVEX, that is your expansion valve, which is something that we haven't really discussed a lot in classes yet. So your thermostatic expansion valve, it regulates the liquid flow into the evaporator. That is to maximize the efficiency of the evaporator, so it kind of gets the vapor and liquid good, so once it goes in the evaporator, it makes it run very successfully and prevents excess liquid returning to the compressor, so no liquid can go backwards into the compressor, causing failures with the compressor. Here is our ideal thermodynamic refrigeration cycle. As you can see, this is your actuals right here. So in an ideal cycle, you want to stay underneath your curve in the TS diagram. And you can also see where the work goes into the compressor. Your QH is coming out of the condenser, and your QL is going into the evaporator. So in an ideal versus real cycle, ideal cycles can be reversible, but it is not necessarily acceptable in the real world applications. The ideal cycle does not account for friction losses in the fluid, as well as the heat transfer to or from the surroundings. So you can add heat transfer loss in pipes and other such things as that. Here's some sample calculations. If we take the temperatures that's recorded on temperature sensors, we can find that, like at the condenser, it's 28 degrees Celsius, and into the evaporator is -10. Here I use 5 kilograms per minute as your flow, and this is your enthalpy values found from the steam tables, and that would give us our work of the compressor. This can also be found as we are putting the direct source into the compressor also. And then the refrigeration cycle capacity, we can find the Qn by using, because H1 is the same for both of them, and we get H3 from the tables. So this is it continued. As you can see, H1 minus H4 on the top, divided by H2 minus H3. I think I accidentally just said H3. But so that's your Qn over your work, and I'll give you your coefficient cycle. Coefficient of performance. And here is an example of a pH diagram. So in the pH diagram, you can see this is your like ideal cycle going here, but in reality, it's actually going to work like this. And that's all I have. Do you have any questions?